Okay, this is lesson 13. So we're just starting our chapter 7, which is the last chapter that we're going to be looking at. And we're going to get through regression analysis for quantitative variables. So part 1 is quantitative variables, and then part 2 is categorical variables and dummy variables. So we'll look at how to enter those kinds of constraints into a regression analysis. All right, so like I said, it's all about linear regression, and this week you'll be working on the homework assignment and upload that to SitLearn. Same as usual, it's an Excel template. It's due Thursday night at midnight. I have given you the videos for that. They're all ready to go. There's only 2 questions. One that's a simple linear regression, and the other one is a multiple linear regression. And then Team 7 also has to do a Zoom presentation for me on companies 40 through 45 in the big data book. So let me know if you have any questions on any of those aspects. All right, so to get us started, this is everything we're doing this week. We're going to start with simple linear regression models, and then we'll talk about these other things, including multiple regression models, as we go through the class. But I want to start by looking at the difference between these two, the simple linear regression and multiple. And then I'll look at an example with you and talk you through some of that so that you can see what all these terms and equations mean, and then I'll come back to the slides. So simple linear regression is a regression analysis for which any one unit change in the independent variable is assumed to result in the same change in the dependent variable. Okay, so X is the independent variable and Y is the dependent variable in terms of graphing it, your X and Y axes. And then multiple linear regression is the same thing. The only difference is that you have multiple independent variables, so multiple X variables. All right, let's look at our first in-class exercise that has to do with simple linear regression. I'll share that file. Okay, so when you get to this, this is your homework file as well. I put them together just like last week. Save this last name, first name, homework lesson 13, and then save it on this purple tab. So when you get to that purple tab, just hit save at the very end before you upload it right there. Okay, so that will meet those requirements. All right, so let's go to this SLR red tab and look at the first example of what we have here. So this is the data that's part of the question, and I've labeled your X and Y variables, right? So X meaning weight and Y is your price. And so what you're trying to determine is, these are bikes, is the bike's weight have any impact on the price? And you would expect that, right? So lighter bikes, these nice aluminum bikes, are a lot lighter than, say, a steel bike, steel frame bike, or other materials. So those lighter weight bikes are your racing bikes, or really high-end bikes. So you'd expect that if it weighs less, it's going to price out higher. Okay, so in our example, what we're looking at is Bicycling World. They're a magazine devoted to cycling. They review hundreds of bicycles throughout the year. Its road race category contains reviews of bikes used by riders primarily interested in racing. One of the most important factors in selecting a bike is its weight. The following data show the weight and price for 10 bicycles reviewed by the magazine. So first you're going to develop a scatter chart with weight as the independent variable. So weight's X on this axis. And then what does the scatter chart indicate about the relationship between the weight and the price of these bikes? So you just highlight this data here, right? So highlight that data and you go to insert, and then you click on that scatter graph right there and you'll get this graph. Okay, so then once you get the graph, let me go ahead and do it. Once you get that graph, if you want to get this trend line on, it's really easy. You just click on one of the dots, right mouse click, add trend line. And then you can add your equation and your R squared if you want, which I think is going to be useful because we're going to talk about those things. And basically what you see here is a downward sloping line. So the slope is negative $1,439. So that means that for every pound that's added to the weight of the bike, this equation is indicating a $1,439 drop in the price. So heavier bikes cost less, right? And then this is the intercept. And I want you to recognize that that intercept isn't necessarily meaningful. Most times it isn't. For instance, here we're talking about a bike that weighs 0 pounds, which doesn't even make any sense. So the cost of a bike that weighs nothing is going to be $28,000, right? It doesn't make any sense. It's just the y-intercept, it's where that line is connecting up with a y-intercept based on this linear relationship. So when you're using this equation that you have here, it's only good within the range of values that you have here. So this is your highest weight and this is your lowest weight. So within that range of weights, this equation would be fairly predictive. So that's what R squared is helping you figure out. R squared is the explanatory, how much of the variance is being explained by the independent variable. So how much of the variance that you see here in the price is being explained by the weight. So we'd say 86% of the variance has been explained. So that's the equation, y equals mx plus b, right? And when you look at the slides, which I'll go back to shortly, you'll notice some of the notation is different than that, but it really means the same thing. So I'll help you connect that up in the video. Okay, so this scatter diagram indicates there may be a negative linear relationship between weight and price. Lighter bikes are generally expected to be more expensive, and the scatter chart is consistent with what we would expect. So B, use the data to develop an estimated regression equation. Well, I already did that here, but we're going to do it using this output that we get from Excel. Okay, what's the estimated regression model? So you go to data, you got to use data analysis. We've talked about this before. If you don't see it, you go to data, go to file, options, add-ins, and data analysis tool pack, add that. So you click that and you put in your, click regression, you put in your Y range, so that's those values, that's perfect. You put in your X range, so that's perfect. You tell it where you want it to go. Whoops, cancel that. Where you want it to go, so I'm going to put it way over here. That's better. And the residual plots, so that you want to make sure you click that. So there's really four areas, the X and Y, 1, 2, 3, 4. So 4 things that you should do there. Okay, so you say okay, and you get this output. I have the same output over here. Let's look at this. So I'm just going to get rid of that. It's okay. I'll get rid of it later. All right. So you notice you got the same R squared that we got when we did it this way. So this, I like to look at it when I add the equation and the R squared valued here is a shortcut to the regression results. This gives us more information, and we do need this information to be able to evaluate whether or not these coefficients that come out of the regression for that straight line, whether that has any predictive value. And obviously the R squared gives us insight into that, right? How valuable this equation is. But these statistics here also give us insight on that. So the equation then would be y is equal to 28818, I'm going to drop all the decimals, minus 1439x, x is the weight, right? So that is the regression equation from these coefficients, which are the same. So this one's put y equals mx plus b. I just did y equals b plus mx. No big deal. In accounting, that's generally how we set it up. So same idea, same equation come out of this model. They're under the coefficients column. So that's the intercept and this is the slope. Okay, then this t-stat and this t-stat are way beyond the critical values for either 1%. So 1%, which is a 99% confidence interval, 1% would have a critical value of 2.58, and a 95% confidence interval or 5% level of significance would have a critical value of 1.96. So both of these t-stats are way out beyond that. Okay, so let me explain a little bit more. What that means is you're going to be able to reject the hypothesis So what is the hypothesis? The hypothesis is that neither the weight doesn't have any relationship to price. And that would mean that this line would be straight across. So no matter what the weight of the bike, the price would always be the same. So there'd be no linear relationship between that, meaning that essentially the slope is zero. So we'd say the slope is zero. Okay, so what's the chance that the slope is zero is what we're saying for a hypothesis. So the hypothesis is that m really is equal to zero. And we can test the intercept too, that b is equal to zero, but it's less important because most of the time b isn't relevant anyways. It's just a number that is inserted into the equation that's a result of the linear lines. Really, this is the hypothesis you want to test, that slope is equal to zero. And if it's outside of those critical values, then you can reject the hypothesis that it is zero and therefore has a linear relationship, either negative or positive. All right, so that's what that's saying. And then these values, notice how small they are. Okay, they're super small. If you change those to a decimal, you can do that by going to home, comma, right? And then changing the spacing. You'll notice these are significantly less than zero. So you would reject the hypothesis that the intercept or the slope are zero. And you notice when you do the confidence interval, zero is not in either of these ranges of number. Okay, so essentially what that's saying is we've got a pretty good model here. It's a fairly strong model at predicting price, given what the weight of the bike might be. All right, another thing you got to look at in order to evaluate whether these are reasonable statistics is the residuals, because there's some other things that could be going on that cause problems with our coefficients. Right, so we want the coefficients to be good predictors. So if we put an x value in, we want that price to be fairly close. So what we calculate is residuals. What a residual is the difference between the actual value of y. So let's look. These are prices for each one of these, right? So these are actual prices. And then these equations would give me a predicted price, predicted y. So this is actual. I could add another column there, must be predicted price. Let me just do one so you can see what I mean. So it's this price, right, times, sorry, this weight, times the 1439. I gotta make that negative, so let me insert a minus. And then you add 2818 and change. Right, there's some decimals on that. That gives you a rough idea. So given the equation, you would expect the price of this bike to be $3,060, but it's not, it's this. Okay, that's what a residual is. A residual is the difference between the actual price and the predicted price. Okay, so if the actual price is more than the predicted price, you get a positive difference. If the actual price is less than the predicted price, you get a negative difference. Okay, so that's what these residuals are, and you plot them and you study the patterns that might exist. Unfortunately, we only have 10 data points here, so it doesn't really, it's not really helpful for me to explain what you're looking for. So what I've done is I've added a tab. Let's take a look at this. So if I had a ton of data points, which I'd really like at least 30 to be able to use the residuals effectively, I'd need at least 30. If I could get more than that, I'd take it. 50 would be awesome. And what I want to see is a lot of randomization in these residuals. I don't want to see any clear patterns or shapes or clustering that's lopsided on one side of the line or the other. I don't want to see anything like that. I want to see something like this. Very random looking data. Okay, and again, residual, these dots are actual value minus predicted value. All right, so here's a graph that would violate the assumptions that we make when we're doing regression analysis. And so it would affect the quality of my coefficients in terms of their ability to predict a value. So this is showing you that the variance in these points, the differences are getting quite large out here as you get into bigger values of x, and they're quite clustered, quite small differences back here. So this would violate one of the assumptions that the residuals have a constant variance, which these would, right? There's fairly equal number of dots on both sides. fairly equal. Doesn't have to be perfect, but just fairly equal. And then B, notice you see this V shape here. So this one suggests the model underpredicts the value of the dependent variable for small and large values. So because you're getting positive residuals, that means the actual is greater than predicted. So you're under predicting, right? It's not big enough. So for large and small values, you'd be under predicting. And then down here in the intermediate range in the middle, you're saying the negative residuals. So negative residuals would be where the actual is less than predicted. So you're over predicting. All right, then C, and again, this would violate your assumptions for using that equation to predict values, right? It would only give you a value, but you might have errors, bigger errors, depending on where you are in X. And you don't want that to show up in your model. You want your model to be good for all the values of X that you're looking at within the range of values. All right, this one also violates one of our assumptions in that you're not seeing the same pattern on both sides of the zero. It's not symmetrically distributed around zero, and that skewness suggests that the residuals are not normally distributed. So here you see the residuals are normally distributed, normally scattered around zero. Okay, so zero error, which is why, see, we want to be able to assume E is zero. So they are out to zero. In this case, they probably don't. Okay, so this is indicating some skewness in the data. And then the fourth one is an independence issue. If you look at every fourth dot, they seem to fall in the same rough, like a small range, a small control area. So for instance, this is the first dot out of 4. So 1, 2, 3, 4. 1 is showing up around the same place. 2 is showing up around the same place. 3 is roughly the same place. 4 roughly the same place. And that pattern repeats and repeats and repeats. So there's definitely something going on. Every fourth point has a relationship with each other, right? There's some problem with independence in the data. All right, so these are the kinds of things that we're looking for when we look at this plot. And again, we only have, what is it, 10 in this one? Yeah, 10 data points. But looking at what we do have, looking at what we do have here, it does look like I don't see any real concerns here. So I would be okay with using the coefficients as the equation and helping us predict values. I don't see any real big issues. Okay, there seem to be equal number on both sides. You know, again, you have to be super careful because there's not enough data points to really say for certain what issues might exist, which is why you want bigger sample size. All right, so then I'm just talking to you about the regression parameters. So here, I'm going to talk to you about what this B1 means, and down here you see B0, and here again, B1. So I'll talk to you more about what that means. So this is referencing the p-value that we looked at here, and it's just saying that that is significant. So we can reject the hypothesis that that's 0, meaning that there is a linear relationship that exists. Okay? So you can read through that if you want to. We talked about this already. R squared is the coefficient of determination, goodness of fit. It explains approximately 80% of the variation in the price of bikes. And there's the equation. For 15-pound elite bike, you would expect it to cost around $72.33. Right? So you take the intercept value you got in the equation, the coefficient for intercept, minus the slope times the number of pounds for that bike to get the answer. That's the expected price given the equation. And it's going to have some variability because not all of the data points are on the line. And so what this is telling you is whether or not you can count on those residuals. And we said a 5% level of significance. So you're willing to make an error 5% of the time, right? Okay. All right, let's go back to the slides real quick, and then we'll come back and do the last one. Okay. So let me walk you through this. the B0, I had said to you that the equation for the regression is using these B indicators instead of what you have been used to with a straight line, the equation for a straight line. So this is the same idea. Y equals the intercept plus the slope on the x variable plus E, that's the residuals, which if the data is normally distributed and the assumptions are all adhered to, you would expect E to be 0. So generally we ignore it because we expect it to be 0 given our assumptions. Okay, so just showing you again a positive linear relationship, and if all the dots are on the line, we'd have an R squared of 1. If they're way off the line, the R squared is smaller. The further out they are, the less power, right? So the smaller they are squared. This is a negative relationship. You saw that in the example with bikes, prices, and weight. And again, if you get an R squared value close to 1, that means all the dots are on the line. If it's less than 1, that's indicating the dots are scattered about the line. And the smaller they are squared, the more scattering there is, right? The less power you have in your equation. This is showing the slope is 0. So this is where you would find that the p-value is greater than the level of significance. There is no linear relationship between the x and the y variable. Okay, so fixed costs are an example of that, where the fixed costs remain the same no matter what level of activity you're at. Okay, so then your least squared method, notice these little b's. The least squared, the little b's substitute for the big b's because you're talking about sample data. Let me go back for just a sec and talk about that real quick. Those are big B's, capital B's, that's for population data. It's characteristics of the population. Whereas the little b's are the sample data, talking about sample data. Okay, so B1 indicates slope and B0 indicates intercept. So that's what that's talking about. All right, then I talked to you about this too, experimental region. So the equation that you got from the regression should only be used when you're looking at that range of values. And the intercept is generally not in that range of values. Oftentimes it's not. And so it's just an extrapolated number outside of the experimental region. And so to use it for any purpose, so for instance, 0 weight bike, that doesn't make any sense, right? It's kind of meaningless. Okay, so that's why it usually involves the intercept value. I showed you how to do this. I showed you how to do a scatter chart too, and get the equation on the chart. And I also showed you how to do it using data analysis toolpack. Okay, and then we talked about coefficient of determination. So I'm not going to make you calculate that by hand. We would do that in Excel, but I do want you to know how to interpret it. So it takes a value from 0 to 1. It will be 1 when all those dots line up on that line. It'll be less than that when the dots scatter about the line. So if you end up with a really low R squared, mostly the data is so highly scattered that really the equation you developed is kind of meaningless because the actual data points are really reflective. The errors are large, right? The errors are large. All right, so now the multiple regression, I want to talk about multiple regression. I'll do that by showing you an example, then we'll come back and finish up slides. Okay, so here's the multiple regression. What do we got? It's Dixie Showtime movie theaters. They own and operate a chain of cinemas in several markets in the United States. Let me fix that. The owners would like to estimate weekly gross revenue as a function of advertising expenditures. Data for the sample sorry, I got typos everywhere. 8 markets for a recent week follow. So A, develop an estimated regression equation with the amount of television advertising as the independent variable, X, and test for a significant relationship between television advertising and weekly gross revenue at the 5% level of significance. What's the interpretation of this relationship? Okay, so I've done a scatter graph of that. This one is just showing you television advertising and weekly gross revenue here. And I dropped the equation and the R squared on just like we did before. And I also ran for that one, this regression statistic. So same R squared as you got up here. same coefficients you got here. And because this R squared is kind of low, I'm concerned that one or both of these maybe isn't statistically significant. So that's why we got to look at these p-values. This p-value indicates that this is not significantly different than 0. Okay, so it doesn't matter anyway for this one because it's outside of our experimental range and it's extrapolated. So I'm not real concerned that this one fails. This one, however, I can reject the null hypothesis that this is 0. And therefore, there does appear to be a linear relationship between television advertising and gross revenue. So this part of the equation, which is the most important part, which is really the slope of this line within this range, is relevant. Okay, that's what that's saying. And that's more or less what I talk about down here in this paragraph, right? Okay, so talk about those levels of significance and just typed out what I just said. All right, then the second part of this question, develop an estimate regression equation with both television advertising and newspaper advertising as the independent variable. So here, we're going to have two x's. So the way you do that is when you do the regression model, make sure when you put in the x variable, you highlight both of those areas for x. When you do the homework, I show you how to do that. Okay, so looking at that data, we'll look at the residuals for that data. Notice you got and you got p-values on those. So this one, again, is not significantly different than 0. Again, I don't care because that's outside of my experimental range. That's the y-intercept, which if you look at the data, right, the range of values is between 3 and 7, and here between 1 and 8. Okay, so I'm not really concerned about that. I'm more concerned about the range of experimental values. These two hold up though at the 5% level. So I can reject that these are 0, right? So these are meaningful coefficients in the equation. So there's the equation. So notice how this looks. Y is equal to the intercept, so you still pull that in, plus this variable times x1 times the amount of television advertising, plus this variable times x2, the amount of newspaper advertising. Okay, and you look at your residuals. Okay, I don't see anything that concerns me terrible about that. And again, it's small data points, so don't get too hung up on it. That one looks fine too. So this is for the television advertising. This one's for the newspaper. And again here, this other one, I don't see any big problems there. There's a little bit of increase in the variance right in here, but then it seems to go away. So I'm not really sure if it's just spurious from having small sample size. Probably is. Okay, so that's really what I wanted you to get from this week's lesson. And then I just kind of wrote up what I said here. So if you want to look that over. Look how much the regression improved by including both of those variables. All right, so one thing I haven't tested for is multicollinearity, which means that there's a high degree of correlation between these two. I could test for that correlation by just doing equals CORELL. Oops, and I did 1L. And just taking a quick peek at that. That's pretty low. All right, so you don't want to have two variables in your multiple regression that have a high level of correlation with each other. Remember, correlation runs from -1 to +1. That's fairly low. And that's why you're getting more power by adding both of them in. You're getting a stronger equation that explains more of the variance. So 93% of the variance is being explained with this new regression, multiple regression, right? So it's a better model than the first model that you had that only had television in it. Okay, and they're not highly correlated with one another. So that means that that variable it's independent, right? There's independence that exists. There's not that one variable doesn't depend on the other variable. There's no correlation between them. So that's something else we can check for. If we notice we throw in another variable and the R squared doesn't change by very much, then you might have problem with multicollinearity, it's called. All right, so anyways, that's about it with multiple regression. Hopefully you got the gist of that. If you need any help with it, let me know. Let me just go back to my slides and wrap things up, and we'll be all set. Okay, so a couple things here. So now look at the equation. This is intercept again. This is the slope on the first variable. This is the slope on the second variable, and so on as many variables as you have. And then you also have the residuals, the error terms that you want to look at. Okay, so there's the regression feature in Excel. Make sure you got these values. You can use labels if you want. You can modify the confidence level. I always click residual plots, so I get those residuals to plot out. I've walked you through this, right? And then I talked to you a little bit about this multicollinearity at the very end there. And I walked you through these graphs, right? So that's what you do want it to look like. If you got any kind of strange looking patterns like these are going to affect the quality of your regression equation, right? If you got issues that are going on that violate the assumptions that you have to make in regression. Okay, so we also talked about this, the hypothesis. So if any of the slopes equal 0, there's no linear relationship. If the slope does not equal 0, then there's something there. There's a linear relationship between them. Okay. I won't make you calculate those test statistics. We got them right off of the Excel table. So we'll just use what we got there. I won't make you calculate p-values. They're right there in the table. So we'll just use what we got. Same with the confidence intervals. Okay. Okay, so this has to do with the multicollinearity. So I talked to you a little bit about that. One way you can kind of get a handle on whether or not that exists is to do a correlation coefficient between the X variables. And if there is high amount of correlation, you're probably not going to get much power from adding it to the regression. If there's low levels of correlation between the variables, then you probably should try it, see what happens. Okay, so just wrapping things up. Make sure you get your homework done by Thursday night, upload that file, and then Team 7, you do have a Zoom presentation you have to make of the big data companies 40 through 45. Okay, so that's all I have for this week. If you have any questions, please let me know. Thanks.